Good morning, everyone, or evening if you're not with us in America. So, thank you for being on our tutorial. Before we get started, I think it's worth registering for the material. And in order to access it, you need to go to oxosemantictech.typeform.com/KGC23. And there you'll be able to access the whole package with data and the RDFox executable, and also a a PDF presentation, which is what I have here. And this will contain lots of useful links and information for you. So yeah. Okay, let me just. So yeah, this takes a couple of minutes to get set up, but so whilst you do that, I can talk a little bit about what the game plan is. There we go. So the objectives for today are to, first of all, set up an RDFox server. This shouldn't be too complicated, and but there's always issues with Windows and Mac and so on. So if anybody is experiencing any trouble, please do write in the chat, and we'll try and help you out. After that, we'll look a little bit at what the data is and why we need what reasoning is all about. And then we'll start looking at SPARQL, first looking at the basics, and then looking at the main idea of the language and exploring some other features. And in the end, we'll look at reasoning and go through a similar cycle where we first look at language and then explore some of its features. In the interest of simplicity, we'll use Datalog, which is a reasoning language that we and some other people use, which, in my opinion, is much easier to use than OWL or Swirl, even though RDFox supports these as well. In the reasoning segment, as I mentioned, we'll proceed along similar lines to the SPARQL segment. So we'll see what the basic idea of the language is, explore some features, and finally talk a little bit about why we need it and how it works in practice. And also, let me reiterate, please feel free to write in the chat or interrupt at any point, and we'll do our best to answer. Okay. So how's everyone doing with with downloading the package and unzipping it? Is everyone okay with that? Okay. So let's move on and see what our data is. Today we'll be using a dataset from Formula One. For those of you who don't know, Formula One is a racing championship, and in fact they raced in Miami 2 days ago. And in our dataset we have drivers, teams, and races that they've been at, and where they've finished in those races, and many other things. Just as you'd expect, the drivers have to try and finish ahead of everyone else to win the race, and we record this information in the data. Now we've taken this data and put together a little demo that you can find at f1.rdffox.tech, and there you can choose your own criteria to define who is the best driver in history and find answers to that. And based on the criteria that you set, the answer may change. So you might have somebody who won the most races, but then you might also have somebody who is better than their teammate most often. So if you're interested and you're waiting for others to get set up, do go and give it a look. Now, because figuring out all these different criteria is quite complex, and we don't want to create a crazy API to do this, The way that we've implemented this is to use reasoning. Okay, so if I go to the next slide, and here we're talking a little bit about why we need reasoning. If I go to the next slide, you can see that we have two queries. One of them is very long and complex, and one of them is pretty simple, really. And I know which one I'd rather write or read. And it's also, as you can see, more than 3 times faster, almost 4 times faster, the one on the right. But what's the difference? Well, how come I can ask the same question in one way or another way, and the results are the same, as you can see? We can do that with reasoning. So, yeah, I guess the basic idea of this is we can take a long and complicated query and turn it into a much simpler one that's faster to execute. So yeah, here these two queries are equivalent, and yet one of them is much better. And reasoning lets us do that. So for everybody who uses graphs but always struggles with maybe data that's a little bit too complex, or is not ready to go into production as it is because the queries are just too slow because they're so complex, then reasoning can provide an answer to that. So let's get set up. By now, hopefully the download of your folder, of your package, has been completed. So you can either open a terminal and cd into it and run AudioFox, or you can do it in Visual Studio Code. So in my case, actually I'm doing it in Visual Studio Code. So I can say that I want to open this folder where my workshop is, and the terminal has already opened. In fact, I can also open it by clicking up here and opening a new terminal, or I can just cd to where my folder is. In this case, AudioFox Workshop KGC, and then I have to run /AudioFox sandbox.start.audiofox. So many AudioFoxes. When I've done that, it will tell me that I have a license that's expiring soon. It will tell me that I've created a data store called F1, and it will tell me that I've imported some data up to 2020. We had 4.5 million triples, and it took 1.14 seconds. I've also started an endpoint at localhost 12.110. So now we can forget about this whole screen. And if I go to localhost 12.110/console, let me just open that. There we go. There we go. I can now see that I have some data. And if I issue this basic query, we see what we have exactly. So is everyone all set up or struggling? Okay, so we have a couple of questions from Laurent. Tom, do you think you could help Laurent with this question? Okay. So moving on, this is the data that we have in the data set. As I mentioned, we can in fact explore a sample of it by clicking on this nice link. Open Google Chrome, there we go. So here we can see a sample of the data. This is by no means all of it. And you can see that there's this driver called Hamilton, who I'm sure many of you will know. And he did a race for McLaren, which was his old team. And this results node tells us that in this race, which is race 18, in this race, his position, there we go, was 1. So basically, he won the race. And also his qualifying was 1, so he qualified before everyone else as well. And this race, what race was it? Well, it was a race on the 16th of March 2008 at 4:30 a.m. UTC, and it was in Albert Park in Australia. So it was the Australian Grand Prix of 2008. So any questions at this stage? No. Okay. I guess we need to maybe wait for Laurent for a couple of minutes.
It took a little while for the emails to come through, and I noticed at the same time.
Yeah.
Maybe show the unzip of the package that we received.
Sure. Okay. Well, for the benefit of everyone else, maybe I can. Go and show everyone the form again. Valerio. Here's my email. Company. Back. And I accept the terms. Now I should have received an email. In 2 minutes. There we go. So Anas is asking about how long the license lasts, and the one that comes with the package lasts for, I think, 4 days. The one that you can get from our website at rdfox.com/tryrdfox for free, all one word. That one lasts 30 days. Okay. Sorry about the fact that it's blocked, Laurent. Maybe we can we can show you at some other stage, or I mean, I guess you'll be seeing it. So are we all ready to move on, or? Okay, terrific.
Ask for a thumbs up from those that are able to get it.
Yeah. Okay. So can everyone give us a thumbs up if they've got that? Okay. See lots of nice thumbs up. Thank you. Yeah. So apology for the little snag. Hopefully we'll be able to proceed faster now. So as I was saying, we've seen a little bit of our Formula One data and a sample, just so we know what we're querying for. And we're ready to talk about what will look within SPARQL. So first the basics of SPARQL, then we look at aggregates, then negation, then filters, and finally binds. And of course, in the next section with reasoning, we'll see exactly how reasoning can help us do away with all of these. So here's our first query. For those of you who don't know SPARQL, SPARQL is a query language for graph databases, in particular triple store / RDF graph databases. The main idea is that we have a where clause that you can see here. Oops. And in the where clause, we specify a pattern that we want to match within the data. And then in the select clause, we'll take various parts of that pattern and return them to the user. So it's a bit like in SQL, except for the words are different, some of them. Now, when we specify a pattern that we're looking for, we can either be looking for something fixed or for something variable. And if something is fixed, then it will be an IRI or a literal. If something is a variable, it will have a question mark before it. So in this case, in this query, we are saying return all the triples because, sorry, match all the triples because both the subject, predicate, and object of the triples we're looking for are variable. So we're not making any restrictions in terms of what we're looking for. And then from all those triples, we want to return all three variables as well. So we want to return the subject, the predicate, and the object. So you can click on this link actually, and it will run it in the console. Yeah, there we go. Sorry for that. So here we have our first query, and we're looking for everything. You can also comment out things by using a hash. In this case, we're saying that there's a driver called Vettel, and his surname is Vettel, and his forename is Sebastian, and his code is VET. And then here we're only returning the first 200 answers, but if we scroll down infinitely, we'll get infinitely many, 4.5 million results. So any questions so far about what the main idea behind SPARQL is? Okay. So if you're all ready to proceed, why don't you give me a thumbs up? Okay, great. So next query we'll look at is a query to find classes of stuff that we have within our data. So here we're introducing two main concepts. In fact, three main concepts. The first one is that we can use an IRI to specify to constrain the triples that we're returning. So in this case, because the middle element of the triple, it's called the predicate, doesn't have a question mark before it, we know that it's an IRI. So it's not, we don't want to just return anything to just match everything. We just want to match all the triples that assign something to a class. Okay. And then the last concept that we introduce is this idea of distinct. So we could return all the different types that are matched, but then if a type is a type of multiple nodes, shall we say, then it will be returned twice. With distinct, we make sure that it's only returned once. So what this query is doing basically is just saying, go and look at all the triples that assign a class to something and tell me what all the distinct classes are. So I can click on that. And here we see it. So we have 13 total classes. We can actually make the screen a little bit bigger. We have 13 classes in total. We have drivers, we have racers, constructors, circuits, seasons, many things. And just to show you what happens if I get rid of distinct, now I get the same type of things many times. So you might want that. In this case, we don't. So, any questions about the idea behind this query? So why might we want to ask this query at all, you might say? The answer is we want to sometimes, when we're exploring our data at the beginning, we want to find out what's in our data, what kinds of triples are there, what classes are there, and so on. And in order to do that, we need to ask all these introductory queries, shall we say, just so we know what's in our data, and then we can find out what the names of the classes are and what they are, and then we'll be able to use those names for queries that are more interesting and that help us answer the questions that we're really after. So next up is a query for finding out all the properties that are associated with a class. Now here we introduce a new concept, which is, in fact, two new concepts, which is the fact that we can shorten IRIs by using prefixes. I'm sure most of you know this already, but for those who don't, I'll just go through it quickly. When we talk about the driver class, it's actually a much longer IRI, which you can see here, and but we shorten it just so we don't have to type it all out. How do we shorten it? We declare a prefix, and that prefix will be just an empty prefix. So if I go up here, you can see that we've declared a prefix, and the empty prefix is this. So basically, when you see colon driver, it's actually https alifox.com, etc. driver. Just so it's easier to keep track of everything. The following concept that we're introducing in this query is the fact that we can use a semicolon to recycle, as it were, the subject of the previous triple. So here, in fact, I can run the query already. Here, our query is, what are all the different properties that a driver can have? Again, this is not really a schema like in SQL, because our drivers don't need to have all those properties, but these are all the properties that at least one driver has. How does this query work? Well, what we're matching is we're matching all the triples that assign something to a driver. So basically, S will be all of our drivers, and then where S is the subject, we are looking at all the other triples. So basically, here we are creating a list of drivers, and then here we are saying for all the drivers in that list, can you tell me the predicate and object for all their triples that they're in? And then from all the predicates and objects, we are returning the list of distinct predicates that we have. So what do our drivers have? They have a date of birth, a country, a full name. Some of them have a father or a sibling or a child. And so we'll be able to explore our data set in this way. Any questions before I move on? maybe you can do a thumbs up if you're ready to move on. Okay. So if I move to the next query, we can start with a little exercise, which you can see either as an exercise or as a completed query. And here we're trying to find out all the forenames and surnames of our drivers as a string. So if I just go to the console, you can see that the query obviously is not valid, and that's because this doesn't mean anything. But now if we edit it, we'll be able to find the drivers as an IRI, but also their forename and surname as strings. So why don't we give everybody a couple of minutes to try this out and see if and see what they come up with, and then I'll go through the solution. So how has everyone got on? Is it clear to everyone how to do this, or not? And if so, maybe I can pick on somebody and they can help me write a solution. How about Brandon Dobele? Sorry.
Right.
Can you hear us, Brandon? Well, actually, you know what? Maybe we don't have. They know their audio is not enabled. Oh, that's useless. Never mind. Okay, well, I'll just go through the solution then. So here we need to say that our driver is indeed a driver. So in this way, we make sure that everybody who is returned is a driver. And then we want to say that the forename is saved as the variable forename, and the surname is saved as a variable surname. When I do this, I get my list, and now there's my driver, but also as an IRI, which is, I guess, clickable, and then a string of his forename and a string for his surname. Okay. So yeah, this is a first query. Congratulations if you've done it. And we can move on to the next one, I suppose. So the next one, we start looking at aggregation. So there's many different aggregates that you can do in SPARQL. You can do count, you can do sum, you can do samples, averages, concatenations, and many other things. Here we'll just look at count because it's the most useful, supposedly. So we can basically run a query that tells us, of course, sometimes it opens in the wrong tab. We can just run a query that tells us for every driver, how many races have they been in. So here we're still trying to match a pattern in the where clause, and the pattern is for a driver, the driver needs to have been in the race. Notice that the order of the edges is important, right? Results driver is an edge that links a result to a driver in this direction, and we can't really do otherwise until we have reasoning, at least. And then we just want to link the result with the race. So these are all the triples we're going to match. But then we're also going to group them. In this case, we're going to group them by driver, because what we're counting is races, and what we're interested in is a list of races per driver. So here we will have a driver in the variables that we've selected, and then a variable called race count, which is nothing else other than the count of the races for that driver. And finally, we can group by descending race count, just so we see the people with most races at the top. And here you see that some pretty familiar names like Raikkonen and Barrichello and Alonso. People have done lots of races, and they've been racing for 20 years. And excuse me, and therefore have a high race count. Towards the bottom, you will see people with a lot fewer races. Any questions about how aggregates work? Can you give me a thumbs up if you're ready to move on? Great. So next query is a query that looks at something called filter not exists. So sometimes we might want to match, as part of a pattern, we might want to match something that isn't there. Okay, so in this case, we have a driver we're looking for drivers who've never been on the podium. How do we know if a driver's been on the podium? Well, we just look at this position order predicate, and if the object of that predicate is 1, 2, or 3, then it means that they finished the race in 1, 2, or 3, which is the podium. And then we want to be able to basically filter that out. So here we're introducing two main concepts, in fact, three main concepts. The first one is that we can do filter not exists and look for a pattern, in this case, people who've been on the podium, and then remove it from our list of drivers with this filter not exists. The second that we're looking for, the second new concept is that we can use filter to say something like the position order needs to be 1, or needs to be 2, or needs to be 3. And the third idea is that we can use in to just say what an item can be in as a list instead of individually. So if I run my query, yes, the presentation slides will be available. I don't know, maybe Tom can share them, or they're going to be available after the session. So here I'm saying basically, tell me my forename and surname for all my drivers, except that this driver cannot have been on the podium. So not exist, basically make sure that this doesn't happen. This is what we're looking for. And as you'd expect, we get a list of people, and they're probably not very famous because, well, they've never been on the podium, so you would never have seen them on TV celebrating. So yeah, this is a very, very useful feature, and one that is not always the most straightforward, and in fact you can nest them one within the other. Yeah, so I'd love to hear your thoughts about this, and if not, I can move on to the next query. Okay, now here we look at bind for the first time, and now we have a pretty complex query, and this is no exercise. So so now we have a query that basically tells us how many races has each driver been in, and how many races have they won, and what percentage do the won races make up compared to the the total races, right? So if I've been in 100 races and I've won 20, I'll have 20% win rate. So as you can see, this query is already quite complex, and we'll see later how to make it much simpler with reasoning. What does this query do, basically? Here we introduce the idea of having nested queries. So here we have this subquery where we find the race count, just like previously. But then we put it inside some braces, and then all that the outer query will see is the list of drivers and race counts. We can do the same with the race wins, but this time we just make sure that they're wins by using position order 1. And here we also introduce a new concept, which is optional. So in this case, we're finding all the drivers and who've been in a race, and if they've won, we'll return them, and if they haven't won, we'll also return them, but the race wins variable won't be there. And then we say what's the surname and forename of the driver, and we can use the bind keyword, which is a star of this slide, to say, well, we concatenate the forename, space, and the surname, and that will be a new driver name variable. So bind is very, very useful. But not only that, we can just say that if there is no race wins for a driver, okay, because they've never won a race, then we want it to be 0, and we will call that variable race wins final. So if a driver has some races, the coalesce function, some race wins, the coalesce function will tell us that race wins final is the same to race wins, right? If they don't have any, then they will be 0, and this is what this coalesce function does. Finally, we have another bind that tells us take the race wins final, divide them by the race count, and that's your percentage. So, I mean, here we have a few flukes for various reasons, but the idea is that we have a lot of people with high percentages, and then towards the bottom, the percentage gets lower and lower. So here we have people who've won maybe 1 race in 12 or 12 in 100. And finally, we should get some people who've never won a race, starting with Alan McNish. Okay. So are there any questions about SPARQL before I move on to reasoning? Terrific. Let me move on then. So here we can do Datalog reasoning with AudioFox. Again, as I mentioned earlier, we're just going to explore what Datalog looks like, and then look at some looks like in general, and then we'll look at some specific features, and then we'll talk about, well, why on earth do we need it, right? The most basic Datalog rule looks like this. So we have we say that we want to see fact A whenever fact B is in the data. So A is true whenever B is true. And then we have this little symbol in the middle. What does it look like in practice? Well, we can say that whenever there is a result that has a race and a driver, which is what our data currently looks like, we might want to just say, well, let's draw a direct link between the driver and the race, which currently isn't there. And suddenly we'll be able to replace every 2 lines of SPARQL that mention result race and result driver. We'll be able to replace that with 1 line. Maybe it doesn't seem that exciting so far, but we'll see why it's important. Another question that people often ask is, well, why do I need to use fancy reasoning and not just any old SPARQL update, which is a write query, by the way? the answer to that is that there are several advantages by using reasoning. Number one is provenance, and explainability. Number two is when your data changes, you don't have to manage all of that. And number three is that reasoning is completely declarative. So if you then have to figure out a procedure in which to apply all your right queries, which can be very difficult indeed. So, without further ado, we can run this query in the console. And as you can see, there is no results. Why are there no results? Well, obviously because this raised-in variable hasn't, this raised-in predicate hasn't been defined yet. How do we define it? Well, I can just go to my rules, which are here. I can see what they are. And I have my rule1.dlog, and I can import it in this way. There we go. And when I do that, it's added the rule. And now suddenly my data is materialized inside the graph. So now I can ask this question, and I don't really have to worry about anything else. Now, here we've only really saved 2 lines. It's one line. We had 2 and now we have 1. So you might say, okay, well, that's rubbish, right? But actually, we can encode as many lines as we want in only 1 line. So here we saved 2. We could have saved 100, really. And we'll see later and we'll see later exactly how to do that. So I guess this will be new for some people. I guess in the poll it says that 6 people out of 14 have never heard of reasoning. I'd be curious to field some questions now from those 6 people, maybe, or even the other 8. Except they can't speak, can they? But they can, I guess, write in the chat and see if they have any questions. So I'll give everyone a minute to ask any questions, and then I'll move on to the next rule. So Paula is asking, are new triples being added to the graph to allow the reasoning to happen? And the answer is yes. When you define a new rule, in this case, the one we've seen, we're saying that whenever we observe a certain pattern, we want to insert a new triple into the graph. And this is what's happened, and that's why we can query it. So Emma is saying, would you be able to demo importing the rule again? Absolutely. So the way you do it is you go through menu, add content. You can choose the file, or you can just, what I do is I just search like this and drag and drop. Now the good news is that you can import a rule as many times as you want, and you don't need to, and it will only be an idempotent operation. So it will only work, it will only be applied once, basically. As you can see, it says, yes, I've seen the rule, but actually you already had it. Kenneth is asking, is logic and reasoning the same in this context? Well, it depends what you mean by logic, but I suppose so. Here we have some logic that we want to specify such that the graph will take the logic and add some stuff in. And the way that this is called is reasoning, and you can do it in Datalog. And so the language for that logic would be Datalog. What else? Anas is asking, why use Datalog and not Swirl? Well, Swirl is quite difficult for most people, and this is a beginner's class, so that's why we chose to use Datalog. We do support Swirl as well, though, if that's something that you're comfortable with. So I'd encourage you to, excuse me, to take a look at that, or you can reach out to me directly, and I'll help you get set up. Brian Granger is asking, would it be right to summarize rules as meta triples that are used to make querying other triples faster and easier? Um, I guess the second part of that is accurate. The first, not so much, because the rules are not triples. They then live within the triple store as triples. They're in a different format. So so they're not meta triples, but also they are meta knowledge. Okay, and this knowledge can be used by the engine to create new triples. I hope that makes sense. Okay, great. So shall I move on to the ninth query? If everyone is ready, and if so, please give me a thumbs up. Awesome. Okay, so there's one more question. So Paula asks, you may have already mentioned, but how are the triples created by the rules maintained? That's a very, very good question, and we'll touch on it later as well. But the idea here is that the engine keeps track of what triples have been derived based on what other triples and also what rules. And it's able to basically say, oh, well, if this triple or this rule changes, then I need to retract that inference that I made. That's really the crux of why reasoning is better than just writing a bunch of updates of write queries, because then you all of that what was what word to choose, all of that maintenance is done automatically by the engine, and you don't have to worry about it, and therefore you won't make any mistakes and so on. So yeah, very good question, thank you. Okay, so I'm going to move on to my second rule, and here we can see that the rule looks similar to the previous one, except now we have 4 lines instead of 2 in the body of the rule, which you can think of as the if part of the rule. But we've also borrowed the filter keyword from SPARQL to just make a restriction on what one of the variables can be. So here we're saying we want a result that talks about arrays and a driver. So basically the driver has been in the arrays, but also the results has a certain position order, and that position order is less than 4. So the result must be a podium, and therefore I can infer that the driver has a podium in that race. How does that work? I can again go to my console, and here we see no triples because, of course, I haven't imported the rule yet. And now if I just go to r2.dlog, drag and drop that, add the rule, it's taken it. You can see a little triangle here because it's telling me that the results that I'm seeing on the screen are no longer fresh, because obviously I made a change to the data store. And now when I rerun it, I can see that suddenly I do have all the drivers who've been in the podium. So now I can make the same query that I made earlier with 4 lines, with only 1 line. And crucially, I don't have to worry about filters either. So if I'm writing this query with an API, I don't need the API to know what a filter is in SPARQL. It can just say, it just needs to be aware of what a podium is. So any questions here? And there's one from Roger. No, here the format of the rules is called Datalog, not Riff. Riff is a different format. Yeah. Okay, so on to the next rule. Here we actually tackle the first, one rule that's very interesting, and this is aggregates. So if you remember, all the way back in, this query, every time that we want to count something and use that count in some other way in another query, we have to do it through this very awful looking inner query. But what if instead of having to do that, we could just have one little line that told us the same information? And of course, as it happens, we can do it. And we do it using this aggregate rule. So basically, we can say, using this aggregate keyword, we say, find me, try and match all the drivers who've ever raced in a race, and then group them on driver, and then take the count of the race and call that race count, and then just insert a new triple saying that the driver has race count, that race count. Also here, notice that we're building this rule on top of a previously defined inference, namely has raced in. Has raced in did not exist in our original data, if you remember, but we've added it with reasoning, and now we can use it in another reasoning rule. So that all goes back to this idea of you declare your rule set in a declarative way and not in a procedural way. And basically that just makes it much easier to create the rules that you need and make sure that they're not in any way that you don't make any mistakes due to that. In fact, for the purposes of RDFox and the algorithm, it doesn't really make any difference what order the rules are evaluated in. Okay, so I'm just going to click on rule again. So again, we see that there's no data, and I'm going to add my rule 3. I can add it. That's worked. Okay, and now suddenly my query, this query to 10 is pretty much equivalent, I think, to this other query. Now, the length is not actually too different, but now we don't have to worry about group by and count. We only have to worry about has race count. But basically, all the difficulty in writing that logic has been shifted from you, the user, or the API, into the reasoning engine, because it's easier for the reasoning engine to manage it. So that's where the value of this lies in. Okay, there's a question from Tanuja. Is it necessary to save a box in RDFox, or can we do the reasoning in memory? That's a good question. So RDFox, the whole system is actually in memory. That's good because it means it has high performance. And in terms of needing a lot of memory, we try to make the system as efficient as possible with memory. So I think this system might be taking maybe, I don't know, 100 or 500 megabytes of RAM, even though it's quite beefy. So yeah, you need to save the A box, which for everyone who doesn't know is the explicit triples, the ones we imported at the beginning. That's in memory, and then the rules also happen in memory, and the consequences of the rules are stored in memory. So it's all done in memory. Anyone else? Okay, can move on maybe. We have a new rule that we can do with aggregates, and this time we are trying to count wins. It's basically the same as the previous rule, except now we want to make sure that the result has position order 1. So it's basically a win. And then we just use a different variable, a different predicate name for the predicate, because it's representing different information. I run my query. Oops. Okay. And then I can import my new rule. Oops. There we go. And now that my rule has been imported, I can see that I can find my race count and my race win count, and it doesn't look any different to any other triples, even though it's encoding much more complex logic. And here we see that, Lewis Hamilton has got the most wins, followed by Schumacher and Vettel. Now, if you're a Formula One purist, you will know that Hamilton actually has 103 wins, but this is just because this data is only valid up to 2020, and we'll see why we've made that distinction later. I think we're a bit ahead of schedule, actually. So if anyone wants to ask any questions, they'd be very welcome. That's where the poll is at. Okay. So 20 votes now. 14 people say they have used reasoning, and that they've never heard of reasoning, and 6 say that they haven't. So it's 70-30. Now, there's also a new poll that Tom made, which is not have you heard of reasoning, but have you actually used reasoning? So if you have some time, go and vote for that. And in fact, we can see that 11 out of 16, in fact, 12 out of 17 people have never used it. So it looks like lots of people have heard of it, but not used it necessarily. Well, I guess you're doing a tutorial now, so you can say that you have used it. Now, Veronique is asking a question. Could you please give us some real-life industry examples of using reasoning? Absolutely. One example that's in industrial manufacturing in Germany is a customer Fester. They obviously have lots of different parts that they produce, and then they assemble these parts one with the other to create a broader solution that does more interesting things. So you could think about it as there's a little battery that connects to a robotic arm that connects to some sort of moving track. So all of these are individual parts, and together they're not very useful. But then, if you want to know, well, what robotic arm fits with what track and fits with what battery, asking that question is not so straightforward. What you can do is you can make the difficult part of asking the question. You can encode that into a rule, and then you put the data and the rule in AudioFox. And what you end up with is a system that knows how two parts are compatible, and you can ask, are these two parts compatible? And you don't really need to worry about asking it at a granular level. You don't need to worry about, do they have the same voltage and the same current, and do they have this? Is the size of this of this part the same as the size of the other one? You don't worry about that, which is boring and error prone. You just say, are they compatible? And all the knowledge about how they can be compatible is encoded in the rules, and it's all managed by the system. Hope that helps. A couple more questions. Emma is asking, are the rules creating new variables built from the data, or can we use for queries? I'm not sure I understand the question, but I guess the rules are taking data that's already there and adding new connections to it. And then you can definitely use them for queries, as I am doing now, right? So these two predicates, they belong to triples that were created with reasoning, and now we can query those triples. I hope that helps. Brian asks, is it possible to automatically derive rules from the data? No, not really. I mean, it's possible. Everything's possible. It's not possible within the system. What you can do is you can either use machine learning or some sort of queries to find out if you want to what rules might make sense. And again, here the field is quite broad and novel, so I guess it's different for everybody. But then once you know what rules you might want, you can encode them in Datalog, and the system will materialize the results and also manage all the inferences through changes in data, changes in rules, and so on. Okay. Okay, Peter has replied also to Brian on the chat. And Veronique again is asking, is that little symbol the only possibility for a rule? I'm not sure what you mean. So when you have a rule in Datalog, you do need that symbol. But you can also have rules in Swirl and in OWL, where they're called axioms, I guess. And they will ultimately be turned into Datalog for the benefit of the system. But you as a human, as a user, can still access them in their other format. And now Paul is asking, is this a reasoning engine that just works this way in RDFox, or do all reasoning engines work this way? Well, RDFox is both a triple store and a reasoning engine, and it's all one package and it's integrated. So it's not like we're connecting a foreign reasoning engine to RDFox. So that's the first part of the question. And do all reasoning engines work this way? No, they don't. There are lots of different approaches that people take to reasoning. Some of them are similar to ours, and they will materialize triples. Some others, they will rewrite the query to incorporate more meaning, but that means the query is slower instead of faster. What else? Some systems, you change rules in real time. You need to reboot the system if you want to do that, and then the rule language that you can use. Most systems will support OWL and Swirl, which we also support, but Datalog is not the same. So we also support Datalog, and in fact, additions to Datalog like aggregation and filters and negation, which we're going to see in a bit. Okay. So I'm going to move on to the next one, which is the second last rule. This is actually one of my favorites to talk about. Okay. There we go. So here we're talking for the first time about, can we encode knowledge? Can we encode that we want to match a pattern that isn't there, just like we did earlier with filter not exists in SPARQL. We can do it with rules here. And why is it useful? Well, because it just makes our life much simpler. And also we can code this extra knowledge that is not so straightforward, and we'll see why in a second. Here, for instance, we're looking at drivers without podiums. How do we do it? Well, we just say we need a driver, being a driver. And then we want to say there must not exist a race such that the driver has a podium in that race. And if the driver is a driver and there is no race where they have a podium, then of course you can infer that they're a driver without podiums. So yeah, we can run that query, and then we can talk about why that's interesting. R5 Okay. Okay, and here we see the same results that we saw with the earlier query, except that now it's much simpler. I think this is the same query, except that you see how much more complex it is. And you have to know about filter and filter not exists and so on. So this is really the key strength of reasoning. Now, let's talk a little bit about this idea of negation as failure. Obviously, we are at the workshop, so we're interested in also the sort of technical stuff. And the technical stuff here is that negation as failure in materialization leads to what we call non-monotonic reasoning. So this means that if I add a triple, I might need to also retract some triples from the inferences. Okay, so you need to have a system that's able to do that. Let's give an example. There is a driver called George Russell, who's never been on the podium in our data set because his first podium was in 2021, so after our data set. So as soon as we add the data from 2021 and 2022, we will see that he now has been on the podium. So we need to remove the fact that he's a driver without podiums from the system, and we need a system that's able to do that. So I can show that, I guess. I can run this query. It says, tell me everything about George Russell. We can see that he has 38 races. We can see what they are. And we can also see that he's a driver without podiums. Look, of course he is. He's never been on the podium, right? But now I can add the data that we need. Yeah. Okay. And when I add the content, you can see that's added almost 400,000 triples in almost no time. And when I rerun the query, suddenly the data's changed. Now he has a race win count. Now he has a bunch of podiums and races. His race count is not 38, but it's 82. And if I look for, you see a driver without podiums, well, it's just not there. So this is another one of the key strengths that I think Paula was talking about. All of the managing of all of the maintenance of the truth is automatically done by the system. You don't have to worry about what happens if I add some data, what happens if I remove some data, what happens if if I change some rules. All of that is taken care of by the system. So we are trying, I guess the idea here is to make the engineer's life or the taxonomist's life or the user's life as easy as possible. So you don't have to worry about all the stuff that you don't need to worry about, but you're limited by technology. So we've seen the incremental reasoning. Okay, we add rules one by one or all at once. Doesn't make a difference. We've seen that you can add data at any point, and the inferences will automatically change if it makes sense to. I guess now is a good time to fill some questions. We have one from Marc-Antoine asking, curious about the non-monotonic part. Are the rules translated to data flow operations? Oh, that's a good question. I'm not sure about that. I'll have to get back to you on that. Actually, can you expand on what you mean by data flow operation? Or maybe I can reach out. Oh, there we go. Event-driven accumulators. Yeah. Why don't I text you later so we can have a better chat about that. Is that okay, Marc-Antoine? Great. Thank you. Anyone else? Cool. Okay. Oh, okay. Brian's got a question. Is another use case for reasoning to find errors? Absolutely. You can define rules that say what an error could be. For instance, I could have I don't know, in banking, I could have a trader who is trading U.S. equities, but they're only allowed to trade European equities, and therefore this is an error, and I need to go and either it's an error with my data, or it's an error within the business, or whatever. But absolutely, you can use reasoning to find errors, and again, especially with errors. In fact, uh, it's really hard to define them in a procedural way. Whereas with reasoning, you can do it in a declarative way, and you can just build up your logic bit by bit, and not worry about how to execute that. Now we're almost well. In fact, we're on our final rule, and here we can just see that we can borrow the bind feature from SPARQL and put it into Datalog to just manipulate variables. In this case, we've defined previously race count, we've defined previously race win count, and now we can take one and divide it by the other, and now we'll have a percentage win count. So if I run this query, in fact, okay, I can import my rule 6. And now I can find out all the drivers who have at least 10 races and what their percentage wins are. And you can see that you have Fangio and Ascari and Clark and Hamilton, all these big names that everyone knows. So yeah, this is it for reasoning. Any questions before I summarize our findings? Okay. Now, in fact, one interesting thing here is that the percentage in this query is slightly different from the percentage in a previous query. I think it's I think maybe this one. No, hold on. Yeah, there we go. So the percentage for Fangio here is 41% in the SPARQL query, but here is actually 47%. And here the answer is that in 100 years ago, maybe 70 years ago, the way that races used to be is that you can compete in the same race with two different cars. So, for instance, you drive a car, the car breaks down, and then you change car and you drive and you finish the race in that car, and that will count as two results. So actually, this percentage that we have with reasoning is much more accurate. And the answer and the reason why is that the data is just so different across the ages that that it doesn't that when we write queries, we only think about it in its modern form, even though it used to be old. Whereas with reasoning, all of that complexity is sort of abstracted away, and we can ask the queries that we really want with the accuracy that we really want. I don't know if there's any more questions. No, maybe I can move on then to the summary. of what we've done. And again, please do feel free to just keep writing questions as and when. So what we've done here is we've basically started with importing some data, all the races between 1950 and 2020. We've added our first rules and materialized it into the system. And then we've started asking queries. Now, we only ask one query at a time, but you could ask as many queries as you have cores at any given time. And because the queries are quite fast, you could reasonably ask a few thousand queries a second, even on a normal Mac. Again, we make a big song and dance about being performant. So if you need performance, you should consider RDFox. And then once the system was ready and we started asking queries, we've also made incremental updates. First of all, when we add rules one by one, that's an incremental update. We don't need to reboot the system every time, right? And then when we add the data, we added 400,000 triples, but instead of taking a couple of seconds, which is what it took the system to begin, it only took, maybe a tenth of a second, because that's the time it took to process that much, even though all the inferences were computed at the same time. And yeah, incremental reasoning, it's for us, it's one of the key advantages of RDFox, and it's one of the things that that people struggle with a lot in the industry. We can import data at any time or rules at any time, or in fact remove them, or remove either rules or data, and RDFox will automatically manage all of that for us. And it does it without needing to reboot. Why do we need that? Well, it just makes our life simpler, but also it can open the door to lots of new things that maybe we can realistically do in the past, like having a system with data and rules, and the system is live and in production, and there are users who ask questions, and sometimes they change data, and they see the results of those changes in real time. So something like that for us would be a win. So here we can see a little bit about RDFox and its approach to reasoning. You can do ontological reasoning that most other triple source with the reasoner can do, except that for materialization, for people who use this materialization like we do, in our experience, the reasoning is just a little bit slower. And then with query rewriting, it's much slower because of the whole paradigm is slower. It has other advantages, but I won't get into that. And then with Datalog and stuff like negation and recursion, you can do lots of things that you can't really do in any other way, like graph analytics, data analytics, constraint validation at a global and local level, and of course all of the above combined. One little final bit so the approach we've taken is to load data, materialize, and do everything in memory. But we can also persist the data to disk, even though all the server will still be in memory. We can still persist it to disk, and then restart from a persistent data store. So if you're worried about persistence, we've had it, and you can use it, and I'm very happy to show you how. What else? We support OWL and Swirl, as I mentioned, and Shackle for constraints validation. I think there was a talk about Shackle either this morning or yesterday. And we offer access control and asset transactions. And we also can connect to external data sources like SQL databases, Solr indices, or CSVs, and many other things. In terms of deployment, this can be interesting for some people. Obviously, we deploy on a laptop or on a server, whether on-premise or in cloud. We have a Dockerized image that we offer. But because the system is so self-contained and light, it can also be deployed on anything like a mobile phone or a Raspberry Pi, basically on edge devices. And we're seeing a lot of activity in that space. Here we can also see one slide about all the different APIs that the server has. You can embed it in a Java application or in a C++ application. And then you can query it through the REST API like we have done right now. And finally, in fact, there is a poll, a survey that you can do at the end for for the benefit of KGC, but there's also one that you can do at this link, so that we can see whether we can improve at all the material in this presentation. And if you're interested in any further resources, here are some links: documentation, free evaluation, our blog, and just a general website. So that's it from us. I'll stay on for another 10 minutes or so to field any questions. But otherwise, thank you very, very much for attending, and I look forward to speaking to you in person or in the chat. Thank you. So, okay, 22 votes, 20 votes. New question by Sarah Livermore. Thank you. I'm pretty new to RDF and SPARQL, but I found this very useful. You were very generous with your time going through the queries. Thanks again. No problem. Thank you for your kind words. If I guess you're remote, but if you're around, let's catch up. Another question from Marc Antoine. Is IDF Star on the roadmap? Well, maybe we could talk about that in a message when I reach out to you. How many people have we still got? Oh, lots of people still on.
I think you can ask the organisers on listening then. She wanted to put up a survey or something.
Yeah. Okay. Well, thanks all. There's just one final survey that Amit would like to do. So if you could just do that, I'm sure it'd be very useful. And thank you all for your time. And I look forward to seeing the ones of you who are here in New York, and the others. Please, you can always message me. I always like talking to new people. So thanks again. Bye. Oh yeah, do follow us on LinkedIn. You can see the link here.